The cosmos is vast beyond comprehension, a silent ocean of dark matter and distant suns, where time drifts slowly and the light from faraway stars whispers ancient stories. Amid this boundless expanse, a new traveler has emerged, 3I Atlas, an interstellar object that has crossed the immense gulf between stars, entering our solar system with a trajectory unlike anything seen before. Its arrival is not merely a celestial footnote, it is a profound interruption to our expectations, a reminder that the universe holds secrets larger than any human imagination. Avi Loeb, the Harvard astrophysicist whose name has become synonymous with bold scientific speculation, suggests that 3I Atlas might not merely pass through our cosmic neighborhood, it might linger, challenging our understanding of gravity, motion, and the very nature of interstellar objects. The first glimpses of 3I Atlas came through sensitive telescopes that traced faint glimmers moving against the backdrop of the night sky. Observers noticed immediately that its brightness varied strangely, hinting at an elongated, possibly tumbling body, its geometry unlike any comet or asteroid catalogued in the solar system. Unlike ordinary visitors, which follow predictable hyperbolic paths, 3 Atlas's movement defied simple expectations, provoking both excitement and unease in the scientific community. Its unusual acceleration, subtle yet measurable, suggested forces at play beyond standard gravitational interactions. Loeb's analysis, precise and methodical, approached the object not merely as a curiosity but as a possible messenger from beyond. His work emphasized a careful review of all available data, combined with an openness to unconventional explanations. While many astrophysicists remain skeptical of his more speculative claims, the elegance of his argument is rooted in fundamental science. When observations resist existing models, they demand new hypotheses. In this context, the possibility that 3I Atlas could remain within the solar system is not mere speculation. It is a question that compels astronomers to reconsider assumptions about capture mechanisms, interstellar drift, and the hidden architecture of our celestial neighborhood. The object's quiet presence, suspended between the known planets and the unknown reaches of space, carries with it both a literal and philosophical weight. It is an anomaly, a visitor from the stars, a reminder of the fragile boundaries of human knowledge. As the first data streamed in, astronomers felt the tension between certainty and wonder, between the mathematical elegance of orbital dynamics and the poetic mystery of a cosmic interloper whose story had just begun to unfold. In the quiet of observatories, beneath the glow of monitors and the hum of analytical instruments, the universe seemed to whisper, "Pay attention, for something extraordinary has arrived, and it may not leave." The initial detection of 3I Atlas unfolded like a scene from a cosmic detective story. High above the Earth's surface, automated surveys scanned the heavens with unblinking precision. Instruments such as the Asteroid Terrestrial Impact Last Alert System, ATLAS, monitored faint points of light, cataloging movements across the dark canvas of the night sky. In October of 2023, the system recorded an object whose motion immediately distinguished it from the familiar parade of asteroids and comets. It was a slender streak, subtle in its glow, yet undeniable, a whisper of light against the vast backdrop of space. Astronomers working at observatories worldwide rapidly triangulated its position. The object's initial detection revealed a speed and trajectory inconsistent with solar system-bound bodies. While comets and asteroids generally orbit the Sun in predictable ellipses or hyperbolic escape paths, this interstellar visitor moved with a slightly anomalous velocity vector, indicating a provenance from the depths of another star system. The excitement was immediate. The celestial community had previously only encountered two confirmed interstellar objects, Oumuamua in 2017 and Borisov in 2019. and each discovery had prompted waves of astonishment, debate, and, in Loeb's case, provocative speculation. The instrument's sensitivity allowed astronomers to measure its brightness fluctuations as it rotated. Observations suggested that 3I Atlas was elongated, perhaps tumbling, with reflective surfaces hinting at complex geometry. Each pulse of light across detectors revealed subtle clues, changes in albedo, unexpected glints, hints of non-uniformity that defied simple classification. Ground-based telescopes collaborated with space observatories, capturing multi-wavelength data that spanned visible, infrared, and near-ultraviolet ranges. Analysts meticulously calibrated for atmospheric distortion, instrument noise, and background stellar contamination, ensuring that every photon counted in constructing a picture of this visitor. The initial human impression mirrored the data's elegance and mystery, a visitor not just passing through, but one that invited careful scrutiny, a challenge to established norms. Observers, in hushed offices and observatories bathed in dim light, recognized the extraordinary rarity of the event. The first glimpses were more than visual records. They were an invitation to contemplate a cosmic stranger whose presence demanded both scientific rigor and philosophical reflection. As images and readings circulated, a quiet sense of anticipation settled over the global community, knowing that the story of 3I Atlas had only just begun, and that the universe had, for a moment, reached across light years to touch our understanding with the faint glow of the unknown. As astronomers continued to trace 3I Atlas across the night sky, its trajectory revealed subtleties that immediately set it apart from known interstellar visitors. Unlike Oumuamua, which followed a sharply hyperbolic path through the solar system and quickly vanished into the depths beyond, 3I Atlas exhibited a motion that seemed to resist simple classification. Initial orbital calculations suggested that its speed, while sufficient to escape the Sun's gravity under normal conditions, appeared slightly lower than expected for a typical interstellar object. Minute deviations in its trajectory hinted at either unseen forces acting upon it or an unusual initial velocity vector, a clue that the object's journey might not be a fleeting one. Analysts began to examine the gravitational influences it experienced. The object's path intersected regions dominated by the pull of Jupiter and Saturn, yet even the powerful gas giants seemed insufficient to fully explain the subtleties in its motion. Computational models were refined repeatedly, incorporating planetary perturbations, solar radiation pressure, and relativistic corrections, but the results continued to challenge expectation. Each simulation deepened the puzzle. Under conventional dynamics, such an object should have either exited the solar system swiftly or followed a clear hyperbolic path. Yet 3I Atlas lingered in a trajectory that seemed almost precariously balanced, suspended between escape and capture. The scientific community's attention turned sharply to these anomalies. Minor as they might appear in raw numbers, they carried enormous implications. If the object were truly slowing or deviating in ways unexplained by gravity alone, it suggested forces or mechanisms previously unaccounted for in interstellar dynamics. Loeb emphasized that even slight non-gravitational accelerations, akin to the subtle pushes experienced by Oumuamua, could radically alter orbital projections. These observations prompted a flurry of studies. Teams across continents recalculated orbital elements, cross-referenced observational data, and sought confirmation from independent instruments. Beyond mathematics, the trajectory ignited imagination. Could an interstellar object, arriving with such precise timing and subtle deceleration, truly remain within the Sun's gravitational embrace? The possibility seemed improbable, yet scientifically tantalizing. Each plotted position, each refined model, suggested a delicate dance, an almost poetic interaction of motion and force that defied immediate comprehension. The universe, in this instance, presented a riddle not of numbers alone but of balance, of possibility and improbability intertwined, and humanity's understanding of interstellar visitors began to shift from assumption to careful reconsideration. Avi Loeb's involvement transformed the discussion surrounding 3I Atlas from routine astronomical observation into a broader scientific dialogue that bridged astrophysics, speculation, and philosophy. Known for his provocative proposals regarding interstellar objects, Loeb approached 3I Atlas with both rigor and an openness to unconventional interpretation. From the outset, he meticulously analyzed the accumulated observational data, precise positional measurements, light curves indicating rotational dynamics, and spectroscopic information revealing surface composition. Unlike many in the field who favored conservative interpretations, Loeb questioned whether the unusual trajectory and non-gravitational accelerations could point to something beyond natural processes. His methodology was exacting. Using computational models, Loeb reconstructed the object's inbound path, comparing it to a range of theoretical interstellar velocities and examining potential interactions with the gravitational fields of the Sun and the outer planets. Every deviation from predicted motion was treated as a meaningful data point. He considered factors such as solar radiation pressure, outgassing phenomena typical of comets, and subtle perturbations from nearby celestial bodies. Where others might have dismissed minor anomalies as observational error or natural variability, Loeb viewed them as clues demanding serious attention. The possibility that 3I Atlas could remain in the solar system was, for him, not merely speculative, it was a hypothesis emerging directly from the data. This position, however, was controversial. Many astrophysicists cautioned against jumping to conclusions about lingering interstellar objects, pointing to prior experiences with Oumuamua and Borisov, whose anomalies had often been resolved through conventional physics or statistical explanation. Yet Loeb's perspective emphasized the value of entertaining low-probability but high-impact scenarios. His insistence on following the evidence, even when it suggested possibilities outside the mainstream, compelled the community to revisit assumptions about interstellar object dynamics, orbital capture, and the diversity of cosmic bodies entering the solar system. Beyond technical analysis, Loeb framed the discussion within a larger scientific and philosophical context. He asked, what if our understanding of interstellar objects is incomplete? What if these visitors can remain, interact, or even carry signatures of processes we have yet to observe? By positioning 3I Atlas at the intersection of known physics and speculative insight, he expanded the narrative from a mere cataloguing of a celestial visitor to a profound inquiry into the limits of human knowledge. The scientific community, whether in agreement or debate, found itself grappling not only with orbital calculations, but with the tantalizing possibility that a stranger from the stars had arrived to linger and to challenge everything we thought we knew about the solar system. The announcement that 3I Atlas might linger within our solar system sent ripples through the scientific community, eliciting both intrigue and skepticism. The notion of an interstellar object entering our neighborhood and resisting a swift departure defied the expectations established by decades of celestial mechanics. Typically, objects from other star systems traverse hyperbolic paths, their velocities and angles rendering capture nearly impossible without precise gravitational circumstances. The mere suggestion that this object could remain orbitally bound, even temporarily, confronted long-held assumptions and challenged the predictability upon which astronomers relied. This scientific shock was amplified by the object's subtle deviations from predicted motion. Observers noted non-gravitational accelerations, tiny yet persistent shifts that could not be attributed solely to solar radiation or planetary perturbations. These anomalies, while numerically small, were significant enough to destabilize traditional models and invite alternative explanations. Could outgassing or comet-like activity account for these forces, or did they hint at phenomena previously unconsidered? The challenge was profound. Any model attempting to account for these discrepancies had to reconcile with both Newtonian mechanics and relativistic corrections, a delicate balance that tested even the most sophisticated computational simulations. Moreover, 3I Atlas's composition and brightness further fueled the astonishment. Photometric observations indicated a reflective surface inconsistent with ordinary cometary or asteroidal material, while spectral data suggested a chemical makeup not easily categorized. The combination of unusual shape, albedo, and motion created a scenario where conventional explanations strained under the weight of observation. It was a rare alignment of factors, trajectory, acceleration, reflectivity, and geometry that collectively suggested this was no ordinary visitor. The paradigm-breaking nature of 3I Atlas extended beyond numbers into philosophy. Scientists were confronted with the uncomfortable realization that nature could produce objects defying neat classification, entities that linger in ways not anticipated by existing theory. In the quiet halls of observatories and the sterile glow of computational labs, researchers felt a blend of wonder and apprehension. Here was a celestial puzzle that resisted simplification, one that compelled reconsideration of what interstellar objects could be, how they interacted with our sun's gravitational domain, and, perhaps, how little we truly understood the vast ocean of space through which they traveled. A central mystery surrounding 3I Atlas lies in its physical composition, a question that speaks directly to its origin, behavior, and the forces acting upon it. Initial observations, primarily through photometry and spectroscopy, suggested a body unlike the majority of known comets and asteroids. Its reflectivity varied in ways that indicated a non-uniform surface, with patches reflecting more light than others, implying a complex and perhaps elongated shape. While most interstellar visitors are expected to resemble icy or rocky bodies, 3I Atlas defied easy categorization. Was it metallic, icy, or a composite of materials unusual even by cosmic standards? These questions fueled speculation and rigorous investigation alike. Spectroscopic analysis provided additional clues. By measuring the light reflected and absorbed at various wavelengths, astronomers sought to determine elemental and molecular composition. Preliminary readings indicated traces of silicates interspersed with possibly organic compounds, yet the ratios and signatures were not entirely consistent with any single known class of small body. These chemical peculiarities raised the possibility that 3I Atlas had undergone processes unfamiliar to solar system standards, perhaps formation in a different stellar environment, exposure to cosmic radiation across interstellar distances, or surface evolution during its voyage. Mass estimation further complicated the picture. Calculations derived from brightness and assumed albedo offered broad ranges, yet the precise mass remained elusive. Its density, inferred indirectly from acceleration anomalies, suggested either an unusually light structure, akin to a porous or hollow body, or unknown mechanisms influencing motion. Such characteristics echoed debates sparked by Oumuamua, where non-gravitational accelerations hinted at unconventional physics or even speculative propulsion, though no conclusive evidence exists. For 3I Atlas, the physical composition is intertwined with its very trajectory, making these measurements critical to understanding whether its lingering is a natural gravitational coincidence or something more enigmatic. Even shape added layers of intrigue. Variations in brightness indicated rotation, but the periodicity suggested complex tumbling rather than uniform spinning, implying an asymmetric form. Photometric models pointed to elongated or flattened geometries, with potential facets reflecting sunlight unevenly. Each rotation offered subtle shifts in light curves, revealing a three-dimensional puzzle that combined motion, composition, and orientation. These insights framed 3I Atlas not simply as a moving point of light, but as a tangible, complex object, a traveler shaped by its journey through interstellar space, yet defying neat classification within our solar system's taxonomy. One of the earliest clues that 3I Atlas was no ordinary interstellar visitor came from the study of its brightness and shape. As astronomers tracked its rotation, they observed pronounced variations in reflected light, a photometric signature that hinted at an elongated, tumbling body rather than a uniform sphere. Unlike most comets or asteroids, whose rotations produce relatively steady light curves, 3I Atlas displayed fluctuations of remarkable amplitude, suggesting a highly irregular geometry. Some models proposed a cigar-shaped structure, reminiscent of Oumuamua, while others allowed for more complex, faceted forms, each face catching sunlight differently, creating a rhythm of brightness that seemed almost deliberate in its irregularity. These luminosity patterns carried implications beyond mere aesthetics. The rotation and shape influenced how solar radiation pressure affected the object's trajectory, potentially accounting for subtle deviations from gravitational predictions. Yet, even after accounting for these forces, anomalies persisted, reinforcing the sense that 3I Atlas was operating under conditions not fully understood. The interplay between its irregular shape and the forces of sunlight and gravity produced a delicate dance where minor variations in orientation could translate into measurable changes in motion over weeks and months. Further intrigue arose from the amplitude of its brightness variations. Large fluctuations suggested a highly elongated form, possibly exceeding 1 kilometer in length, while remaining narrow along other axes. Such dimensions are uncommon among interstellar visitors, which tend to be smaller fragments ejected from distant systems. The notion of a larger-than-expected body, spinning in an irregular pattern, added to the scientific puzzle. Not only was its trajectory anomalous, but its physical presence challenged preconceptions about the size and shape distributions of objects capable of traversing interstellar distances. Astronomers also considered rotational stability. Tumbling bodies experience complex internal stresses, and their structural integrity must withstand both centrifugal forces and potential collisions with micrometeoroids or interstellar dust. That 3I Atlas had survived these conditions across light years and still maintained a coherent structure, suggested either exceptional durability or a fortuitous avoidance of destructive encounters. Each observation, each flicker of reflected light, contributed to an evolving portrait, a solitary, elongated wanderer, spinning irregularly yet resiliently, holding secrets about its origin and journey that could redefine understanding of the interstellar population. Beyond visible light, infrared and thermal observations revealed further complexities of 3I Atlas, providing insights into its composition, size, and energy balance. Space-based telescopes, including the Spitzer Space Telescope and NEOWISE, measured the heat radiated by the object, allowing astronomers to infer its surface properties. Unlike many small solar system bodies, whose thermal signatures correlate closely with known albedo and composition models, 3I Atlas presented anomalies. Its infrared emissions suggested either a higher-than-expected reflectivity or an unusual thermal inertia, meaning the surface retained heat differently than typical cometary or rocky bodies. These findings raised questions about surface texture, density, and even the potential for layered structures, with variations between reflective and absorptive materials. Thermal data also supported evidence from photometric studies. As the object rotated, the distribution of heat across its surface fluctuated in ways inconsistent with a homogeneous body. Certain facets appeared to retain warmth longer, while others cooled rapidly, implying differences in material composition or porosity. Such heterogeneity could indicate a body that experienced complex formation processes, perhaps originating in a stellar system with chemical diversity or subjected to long-term cosmic radiation that altered surface layers unevenly. These thermal fingerprints became critical for modeling the object's trajectory, as solar heating can produce minute outgassing or photon-driven forces that subtly accelerate or decelerate the body. Moreover, infrared observations helped refine size estimates. Visible light alone is influenced by reflectivity, potentially skewing perceptions of scale. Thermal emissions, however, respond to surface area and energy absorption, providing a complementary metric. Analyses suggested that 3I Atlas could be larger than initially thought, its elongated shape amplified by irregular surface geometry. The combination of reflected and emitted light painted a picture of a body both physically substantial and thermally complex, challenging prior assumptions about interstellar travelers as small, icy fragments. These thermal characteristics fed directly into the ongoing debate about the object's nature. Could outgassing, akin to cometary behavior, account for its non-gravitational accelerations? Or did the thermal anomalies hint at unknown mechanisms influencing motion, possibly connected to exotic composition or structural peculiarities? Each new infrared measurement added a layer of depth to the mystery, reinforcing the impression that 3I Atlas was a visitor not just from another star, but from a place whose materials, forces, and history were subtly but profoundly different from the solar system's familiar objects. The heat it radiated was more than energy. It was a signal, a whisper of distant origins, a tangible marker of its interstellar journey and the enigmas it carried along the way. Among the most perplexing observations of 3I Atlas were subtle accelerations that deviated from predictions based solely on gravity. As astronomers charted its course across months, tiny but measurable non-gravitational accelerations became evident. These were not the dramatic bursts one might associate with active cometary jets, but rather gentle nudges, persistent, directional forces that influenced its trajectory in ways not easily explained by standard models. Such anomalies echoed the mystery of Oumuamua, where researchers grappled with unexplained accelerations, prompting debates ranging from natural outgassing to speculative propulsion mechanisms. The initial hypothesis focused on conventional astrophysical causes. Could asymmetric outgassing, where sublimation of ices produces reactive thrust, explain these shifts? In typical comets, jets of gas and dust emerging from sunlit surfaces can induce measurable accelerations, altering orbital paths subtly over time. Jet 3I Atlas presented no detectable coma or tail, even under sensitive observation. Infrared and optical imaging failed to reveal significant material emission, leaving scientists puzzled. If traditional outgassing was insufficient, the source of motion had to be re-evaluated, prompting careful scrutiny of other potential forces. Radiation pressure offered a secondary consideration. Photons from the sun exert minute but continuous forces on exposed surfaces, particularly if the body is low in mass or possesses a high area-to-mass ratio. For an elongated or irregular object like 3I Atlas, such forces could contribute to deviations in motion, However, calculations incorporating shape, reflectivity, and rotation indicated that radiation alone could not account for the observed accelerations fully. The subtlety of the forces, combined with the object's apparently substantial size, suggested a mystery that straddled the line between known physics and the possibility of unusual properties. These acceleration anomalies carried profound implications. They directly influenced the projections of the object's trajectory and its potential to remain within the solar system. Each measurement, each tiny deviation from gravitational predictions, required recalibration of models and challenged astronomers to question assumptions. The phenomenon highlighted the delicate interplay of forces acting on interstellar objects, revealing how even a slight imbalance can have magnified effects over astronomical distances. In observing these subtle nudges, scientists confronted the profound complexity of the cosmos, a solitary traveler, invisible to all but the most precise instruments, moving according to rules that may extend beyond conventional expectations and inviting reflection on the hidden mechanics that govern celestial wanderers. Perhaps the most provocative interpretation of 3I Atlas emerged from Avi Loeb's consideration of a potential artificial origin. Unlike conventional celestial bodies, 3I Atlas exhibited a combination of features: its trajectory, acceleration anomalies, elongated shape, and reflective properties that some argued could be consistent with a manufactured object. Loeb approached this hypothesis not as sensationalism, but as a reasoned exploration of possibilities grounded in observation. By entertaining the notion that interstellar objects could include probes or artifacts, he emphasized that science must remain open to low-probability, high-impact scenarios, provided they are rigorously tested against empirical data. This line of inquiry did not suggest indiscriminate speculation. Rather, it arose from the convergence of anomalous characteristics. The object's non-gravitational acceleration, absence of detectable outgassing, and unusual light curves collectively invited consideration of alternatives beyond natural formation. Loeb proposed that if such an object were a relic of another technological civilization designed to traverse interstellar distances, its persistence in the solar system could reflect engineering rather than chance. The hypothesis provided a framework for designing observational tests, searching for artificial light reflection patterns, unusual surface composition, or other indicators inconsistent with natural celestial mechanics. The scientific community responded with caution and debate. Many researchers emphasized that extraordinary claims require extraordinary evidence, and that natural explanations, though elusive, remained more probable. Critics highlighted the risks of anthropocentric bias projecting human technological concepts onto an alien object and urged restraint in interpretation. Yet, even among skeptics, Loeb's approach prompted valuable inquiry. By formulating testable predictions, encouraging multi-wavelength observation, and challenging assumptions, the hypothesis served as a catalyst for renewed scrutiny of interstellar object behavior. In contemplating artificiality, the discussion inevitably touched on philosophical dimensions. Could a solitary object, voyaging across the galaxy, be a deliberate emissary, a message embedded in motion? Even if purely speculative, the idea forced scientists to grapple with the limits of inference and the breadth of possibilities in a universe far older and larger than human experience. The consideration of artificial origin, whether ultimately confirmed or refuted, to reframed 3I Atlas, not merely as a passive visitor, but as a focal point for scientific imagination, a bridge between empirical rigor and the profound wonder that arises when we confront objects that may challenge our understanding of natural and artificial boundaries alike. To understand the uniqueness of 3I Atlas, astronomers placed it within the historical context of known interstellar visitors. Prior to its discovery, only 2 confirmed objects had traversed our solar system from other star systems: Oumuamua, detected in 2017, and comet Borisov in 2019. Each provided insights, but also highlighted the rarity and unpredictability of such encounters. Oumuamua, with its elongated shape, unexplained acceleration, and lack of detectable outgassing, challenged conventional classification, while Borisov appeared more like a typical comet from a distant stellar nursery, reinforcing expectations of icy interstellar fragments. 3I Atlas, however, combined the enigmatic aspects of its predecessors with new, unprecedented anomalies, cementing its status as a singular object of study. Comparative analysis illuminated both similarities and divergences. Like Oumuamua, 3I Atlas exhibited non-gravitational accelerations and irregular brightness variations, suggesting complex geometry or rotation. Yet unlike its predecessor, it showed signs of lingering within the solar system rather than following a swift hyperbolic exit trajectory. Its potential size and reflective properties also differed, suggesting a composition or surface morphology not observed in prior interstellar objects. Borisov, by contrast, reinforced conventional expectations. Its visible coma and well-characterized orbital path aligned with models of icy interstellar comets. In this juxtaposition, 3I Atlas emerged as an anomaly that defied simple categorization, bridging known phenomena and the tantalizing possibility of new physics or exotic origin. Historical perspective also emphasized the evolving capability of astronomical observation. Each interstellar visitor's detection reflected advancements in instrumentation, computational modeling, and global coordination. Oumuamua was discovered using the Pan-STARRS telescope, Borisov, via amateur observations verified by professional follow-up, and 3I Atlas benefited from sophisticated automated surveys like ATLAS, coupled with rapid multi-observatory collaboration. This continuum illustrated not only the increasing likelihood of detecting such objects, but also the depth of data now available, enabling detailed analyses of shape, motion, composition, and subtle anomalies. By situating 3I Atlas within this lineage, scientists could better appreciate its significance. It was not merely another transient visitor, but part of an emerging pattern of interstellar objects that challenge assumptions, stretch the boundaries of classification, and provoke questions about the diversity of material and dynamical histories in our galaxy. Each prior encounter provided context, a baseline against which the unprecedented features of 3I Atlas became more apparent, sharpening the sense that humanity was witnessing a rare and compelling chapter in the ongoing story of cosmic discovery. Understanding why 3I Atlas might remain within the solar system requires a careful examination of celestial mechanics and the subtle interplay of gravitational forces. In typical scenarios, an interstellar object enters with sufficient velocity to pass through the Sun's gravitational sphere of influence and continue into the void beyond. Only under rare circumstances, precise alignment, velocity, and timing, could such an object become temporarily bound, caught in a delicate balance between the Sun's pull and its own inertial motion. 3I Atlas, with its unusual trajectory and subtle accelerations, seems to approach this exceptional scenario, prompting astronomers to scrutinize the dynamics that could permit such lingering. Gravitational interactions with the giant planets play a critical role. Jupiter and Saturn, the solar system's most massive bodies, exert powerful perturbations that can deflect or accelerate passing objects. In some cases, these encounters can adjust velocities just enough to transition a hyperbolic trajectory into a quasi-bound orbit, allowing an interstellar object to spend decades or centuries in the outer solar system before eventually escaping. Preliminary simulations for 3I Atlas indicate that while its path is not a stable orbit in the conventional sense, repeated gravitational nudges from the gas giants could sustain its presence longer than would otherwise be expected. The object's own non-gravitational accelerations, whether from subtle outgassing, radiation pressure, or other unknown forces, further complicate predictions. These forces, though minute, act cumulatively over time, slightly adjusting its velocity vector and potentially enhancing the likelihood of temporary retention. Accurate modeling requires integrating both Newtonian and relativistic mechanics, accounting for the effects of the Sun's radiation, planetary perturbations, and the object's rotation and shape. Each factor contributes to a scenario in which 3I Atlas might linger in a quasi-stable corridor, suspended between escape and gravitational capture. This dynamic interplay challenges assumptions about interstellar object behavior. It demonstrates that even a solitary body, traversing vast distances at incredible speeds, can experience a complex gravitational ballet, influenced by forces both understood and enigmatic. The solar system is not a passive arena, it is an active participant, shaping the trajectories of visitors in subtle but profound ways. In contemplating 3I Atlas's potential retention, scientists are reminded that celestial mechanics is not merely a set of equations, but a narrative of motion, timing, and cosmic balance, where chance and structure intertwine to create moments of profound astronomical intrigue. Spectroscopic analysis became a cornerstone in unraveling the mysteries of 3I Atlas, offering a window into its chemical and mineralogical composition. By dispersing the light reflected from its surface into constituent wavelengths, astronomers could infer the presence of various elements and compounds, constructing a tentative profile of its material makeup. The spectra revealed features both familiar and puzzling. Silicate bands consistent with rocky bodies, faint traces suggesting organic compounds, and peculiar absorption lines that did not neatly correspond to any well-known class of solar system objects. Each signature was a clue, a fragment of the object's history embedded in light. The surface chemistry held profound implications for understanding its origin. Certain spectral characteristics suggested formation in an environment rich in complex molecules, perhaps within a planetary system orbiting a distant star. Exposure to interstellar radiation could have altered surface layers, producing exotic compounds or darkening materials in ways rarely observed locally. Comparisons with Oumuamua and Borisov indicated that while some features were consistent across interstellar bodies, 3I Atlas's spectrum displayed anomalies that reinforced its uniqueness. Its light suggested not merely a foreign origin, but a distinct evolutionary path, shaped by conditions beyond the immediate reach of the sunday. Spectroscopy also intersected with dynamical observations. Variations in brightness and rotation could be partially explained by surface heterogeneity revealed in spectral analysis. Reflective facets might correspond to silicate-rich areas, while darker regions absorbed more light, influencing both observed luminosity and thermal response. These correlations allowed astronomers to refine models of its shape, rotation, and surface topology, connecting composition with motion in a multi-dimensional picture. Each measurement reinforced the sense that 3I Atlas was a complex, heterogeneous body whose behavior could not be fully explained by standard templates of comets or asteroids. Beyond the immediate scientific data, the spectroscopic findings invited broader speculation. Could unusual chemical signatures indicate processes unknown to solar system formation, or perhaps hint at prior interactions with radiation or material fields in its home system? While natural explanations remain most likely, The diversity observed reinforced the object's enigmatic nature and fueled ongoing observation campaigns. Every wavelength captured, every absorption band measured, transformed 3Alice from a mere point of light into a tangible, chemically rich entity, an emissary carrying stories from a distant stellar neighborhood, encoded in the subtle language of photons. Timing, in the cosmic sense, is as crucial as trajectory, and the arrival of 3I Atlas occurred during a period of unprecedented observational opportunity. Modern astronomical infrastructure, encompassing automated survey telescopes, space-based infrared instruments, and rapid global coordination among professional and amateur astronomers, allowed the object to be scrutinized from multiple perspectives simultaneously. Its entrance coincided with a phase in which the outer planets, particularly Jupiter and Saturn, were positioned to subtly influence its path, enabling precise measurements of gravitational perturbations. The convergence of these factors made the detection and analysis of 3I Atlas not only possible but extraordinarily detailed compared to previous interstellar visitors. The object's timing also enhanced opportunities for multi-wavelength study. As it passed through regions of varying solar illumination, instruments could capture both reflected sunlight and emitted infrared radiation at optimal angles. This enabled astronomers to construct high-resolution models of its shape, rotation, and surface heterogeneity. Without such timing, key subtleties like the slight accelerations that hint at unusual forces might have been obscured or misinterpreted. The serendipity of its arrival underscored the delicate interplay between cosmic chance and observational readiness, reminding scientists of the fortuitous alignment of circumstances that permits rare insights into interstellar phenomena. From a human perspective, the timing amplified philosophical and emotional resonance. Just as astronomers had refined techniques in the wake of Oumuamua and Borisov, the solar system presented a visitor at a moment when humanity was ready to receive and interpret it. The convergence of technological capability and cosmic arrival created a unique window for reflection. Here was an object shaped by eons of interstellar travel, now intersecting with the precise epoch of human observation. Each measurement became not merely a data point, but a temporal dialogue between distant stars and our instruments, bridging immense spans of space and time. This cosmic timing further informed projections of 3I Atlas's potential lingering. By entering the solar system during a period of gravitationally favorable alignments and optimal observational conditions, its path could be more accurately tracked, allowing simulations of quasi-bound orbits and long-term evolution. The precise moment of arrival, combined with subtle accelerations and trajectory anomalies, hinted that the object's story would unfold gradually, offering a slow revelation of its secrets. In this way, timing became both a scientific variable and a poetic element, emphasizing the synchronous dance of celestial mechanics and human inquiry that allows the mysteries of the universe to be glimpsed with clarity and awe. Scientific controversy emerged almost immediately as 3I Atlas captured widespread attention. While the object's unusual characteristics fascinated many, they also prompted a spectrum of critical responses from the astronomical community. Traditionalists emphasized the rarity of drawing conclusions from limited data, warning against overinterpretation and cautioning that anomalies often resolve with additional observation or refined modeling. Others acknowledged the peculiarity of the object, but suggested natural explanations, such as subtle comet-like outgassing, unmodeled gravitational perturbations, or observational artifacts, could account for the irregularities without invoking exotic scenarios. Published critiques appeared quickly in peer-reviewed journals and preprint servers. Some studies focused on orbital mechanics, demonstrating that small errors in initial position or velocity estimates could significantly influence long-term projections, potentially explaining apparent quasi-bound behavior. Others scrutinized photometric interpretations, arguing that brightness fluctuations might arise from rotation combined with irregular albedo rather than extreme elongation. Each critique contributed to a rigorous scientific discourse, forcing proponents of alternative hypotheses, including Avi Loeb, to clarify assumptions, refine models, and quantify uncertainties. Despite criticism, Loeb and his collaborators maintained that the convergence of multiple anomalies, trajectory, acceleration, shape, and reflectivity, was unlikely to be coincidental. Their arguments emphasized that even if each factor individually could be explained through conventional processes, the combination warranted serious investigation. By framing the discussion around cumulative evidence rather than isolated observations, Loeb highlighted the need for open-mindedness, tempered by empirical scrutiny. This approach resonated with a broader philosophy of scientific inquiry. Anomalies are not failures but invitations to expand understanding, challenge assumptions, and explore the boundaries of knowledge. The controversy also underscored the sociological dimension of science. Debates were conducted not only in journals and conferences but across media platforms, where public fascination intersected with professional discourse. Avi Loeb's prominence amplified attention, eliciting both admiration and skepticism. The discourse illuminated a tension intrinsic to science, between caution and curiosity, between conservatism and exploration. In the case of 3I Atlas, the debates themselves became part of the object's story, reflecting humanity's struggle to interpret phenomena that straddle the familiar and the unprecedented, challenging both intellect and imagination. Amid the debates and analyses, theoretical models emerged to account for 3I Atlas's unusual behavior, each seeking to reconcile observation with known physics while allowing for plausible extensions. One of the foremost proposals centered on gravitational capture mechanisms. The object's velocity, combined with perturbations from Jupiter and Saturn, could allow it to enter a temporary quasi-bound orbit. Simulations suggested that slight variations in initial conditions, amplified by planetary influences, could sustain a trajectory lingering within the outer solar system for decades. This scenario required precise alignment, a cosmic coincidence, but remained within the realm of classical mechanics, offering a natural explanation without invoking exotic processes. Other models considered the role of non-gravitational forces. As with Oumuamua, small accelerations arising from solar radiation pressure or minimal outgassing could subtly adjust velocity over time. For an object with high area-to-mass ratio or unusual shape, these minute forces accumulate, producing measurable deviations in trajectory. Computational analyses incorporated photometric and thermal data to estimate the magnitude of such effects, revealing that even modest asymmetries in shape or surface reflectivity could influence motion significantly. These models demonstrated that subtle physical characteristics, combined with gravitational dynamics, could account for the observed anomalies without requiring speculative physics. Speculative but scientifically grounded hypotheses also gained attention. Some theorists entertained exotic compositions or structures lightweight, possibly hollow or porous bodies that respond more readily to radiation pressure, or materials with unusual reflective properties that amplify subtle accelerations. Others proposed that 3I Atlas might harbor unique physical interactions, such as charge distribution or magnetically influenced motion, though such explanations remain largely theoretical. Each model, whether conventional or exotic, contributes to a framework for testing predictions against ongoing observations, emphasizing the iterative nature of scientific inquiry. Ultimately, these theoretical frameworks do more than explain anomalies, they provide a roadmap for further research. By outlining potential mechanisms, each model guides observational priorities, spectroscopic measurements to test composition, photometry for rotational dynamics, and precise astrometry to monitor subtle accelerations. In this sense, 3I Atlas is not merely a passive object to be observed, but an active catalyst for refining theory, challenging assumptions, and expanding the scope of astrophysical understanding. Through these models, the object transitions from anomaly to instrument, a tool for probing the limits of interstellar dynamics and the boundaries of current knowledge. Beyond conventional and moderately speculative models, some researchers turn to the frontier of theoretical physics to explore explanations for 3I Atlas's anomalous behavior. Concepts such as dark energy, modifications of gravity at small accelerations, or interactions with exotic interstellar media were considered as potential contributors to its trajectory and lingering. While these ideas remain highly speculative, they reflect the necessity of pushing theoretical boundaries when confronted with data that strains existing models. The presence of subtle, persistent accelerations, combined with unusual brightness variations and shape, provides a rare empirical anchor for exploring these otherwise abstract concepts. One area of particular interest involved the potential influence of dark energy or variations in the local gravitational field. Dark energy, the mysterious force driving the accelerated expansion of the universe, is generally considered relevant only at cosmological scales, yet some theoretical frameworks suggest that local interactions, albeit weak, could manifest in measurable deviations for low-mass, high-area objects traversing interstellar space. In 3I Atlas's case, the hypothesis is far from proven, but the object's anomalous motion provides an unprecedented laboratory for contemplating how fundamental forces might operate in unusual contexts, even within the confines of our solar system. Other theoretical explorations focused on exotic material properties or structural anomalies. Could 3I Atlas possess internal densities or configurations that respond to gravitational or radiative forces in unexpected ways? Could quantum-level effects, magnified over vast interstellar travel, subtly influence trajectory? While such notions stretch beyond mainstream astrophysics, they illustrate the creative interplay between observation and theory. When empirical data resists explanation, even the most speculative frameworks become tools for inquiry, guiding targeted measurements and refining the parameters that must be tested. These ventures into exotic physics are not mere flights of fancy. They illuminate the profound challenges and opportunities posed by interstellar objects. Each hypothesis, whether confirmed or discarded, refines the boundaries of knowledge and sharpens observational strategies. In considering the role of dark energy, unusual structural properties, or other high-level phenomena, scientists confront the interface between known and unknown, applying rigor to speculation. 3I Atlas thus becomes more than a visitor. It is a catalyst, urging the community to examine foundational assumptions, to probe the limits of celestial mechanics, and to contemplate forces that may operate quietly yet persistently across the interstellar void. Observational campaigns quickly intensified as the scientific community recognized the unique opportunity presented by 3I Atlas. Global networks of ground-based telescopes coordinated with space-based platforms to capture a comprehensive dataset across multiple wavelengths, enabling continuous monitoring of its position, brightness, rotation, and potential emissions. Instruments such as the Very Large Telescope, VLT, the Hubble Space Telescope, and infrared platforms like NEOWISE were mobilized to provide complementary views while robotic survey telescopes like Atlas ensured precise tracking of its motion through the outer solar system. This orchestration represented one of the most concerted observational efforts for an interstellar object, reflecting both the object's scientific significance and the urgency of capturing ephemeral phenomena. The campaigns focused on several key objectives. First, precise astrometry aimed to refine orbital parameters and detect minute deviations indicative of non-gravitational forces. Each positional measurement, accurate to fractions of an arc-second, contributed to iterative models that projected the object's trajectory, evaluating the likelihood of prolonged retention within the solar system. Second, photometric monitoring sought to understand rotational dynamics, shape, and surface heterogeneity. Continuous light curves provided data on spin rate, tumbling behavior, and reflective variability, offering clues to the three-dimensional structure of the body. Third, spectroscopic and infrared observations aim to identify chemical composition and thermal properties, informing models of density, albedo, and potential outgassing or radiation-driven accelerations. Beyond data collection, these campaigns enabled cross-validation. Independent observatories confirmed measurements, reducing the possibility of observational artifacts or biases. Data sharing and collaborative analysis fostered a rigorous environment in which competing models could be tested against consistent, high-quality observations. This collaborative effort highlighted the increasingly international and multidisciplinary nature of contemporary astronomy, where objects like 3I Atlas catalyze coordinated scientific inquiry across continents and platforms. The scope of these campaigns also underscored the rarity of the opportunity. Few interstellar objects have entered the solar system with sufficient proximity and brightness to permit such detailed scrutiny. 3I Atlas's presence during a period of advanced observational capability allowed the capture of subtle phenomena, tiny accelerations, reflective anomalies, rotational irregularities that might otherwise have gone unnoticed. In this sense, the object's lingering is not only a subject of theoretical and philosophical fascination, but a practical boon for science, offering a live laboratory to test models of interstellar dynamics, material composition, and the limits of observational astronomy. Computational simulations became an indispensable tool for understanding and predicting 3I Atlas's trajectory. Astronomers and astrophysicists employed sophisticated N-body models to integrate the gravitational influence of the Sun, planets, and even minor solar system bodies, while simultaneously accounting for observed non-gravitational accelerations. These simulations allowed researchers to explore numerous scenarios, varying initial velocities, angles of approach, and assumptions about shape, mass distribution, and reflective properties. By iterating across millions of potential pathways, scientists aim to delineate the range of plausible futures for the object, whether it would eventually escape the solar system, remain temporarily bound, or interact subtly with outer planets. The predictive models incorporated high-fidelity datasets from both ground and space-based observatories, ensuring that simulations reflected the most accurate positional and photometric information available. Each integration step accounted for the complex gravitational ballet between 3I Atlas and the giant planets. Jupiter and Saturn, in particular, exerted the strongest perturbative effects, capable of nudging the object into slightly altered orbits over months and years. Researchers also considered solar radiation pressure and thermal forces derived from infrared observations, applying these subtle influences cumulatively to assess their impact on long-term stability. These simulations revealed delicate balances. In many runs, the object's trajectory hovered near quasi-stable corridors, regions where gravitational and non-gravitational forces nearly counteracted, allowing it to linger far longer than a typical hyperbolic interstellar object. Even minor changes in assumptions, slightly different albedo, mass, or spin rate produced divergent outcomes, highlighting the sensitivity of interstellar dynamics to small parameters. The models suggested that 3I Atlas's observed trajectory could plausibly lead to temporary retention in the outer solar system for decades, though certainty remained elusive. Beyond raw prediction, simulations also guided observational priorities. By identifying regions where the object's path was most likely to diverge, or where subtle accelerations would be amplified, astronomers could allocate telescope time efficiently, capturing critical data to refine models further. In this way, computational forecasts became a dynamic dialogue between theory and observation, each informing and constraining the other. 3I Atlas, in essence, became a moving laboratory, a rare interstellar experiment unfolding across the solar system, whose trajectory not only challenged understanding but also inspired a coordinated, predictive, and methodical scientific response. The lingering presence of 3I Atlas raises questions not only of celestial mechanics, but also of potential risks and consequences for the solar system. While the object's size and distance preclude immediate danger, its prolonged residence prompts careful consideration of long-term gravitational interactions. Even small perturbations can, over decades, subtly influence the orbits of minor bodies in the outer solar system, potentially nudging distant asteroids or Kuiper belt objects into new trajectories. These shifts are minor and largely theoretical at this stage, but they underscore the interconnected nature of celestial dynamics. A solitary interstellar visitor passing through the periphery of the solar system can ripple outward, influencing otherwise stable systems in imperceptible yet measurable ways. The question of potential impacts extends beyond physical collisions. Interstellar objects serve as probes, bringing material from other star systems into proximity with our own. Dust, ice, and other compounds embedded within 3I Atlas could seed scientific discovery, offering chemical and isotopic information about distant stellar environments. Sampling or observing such material allows comparisons with solar system bodies, informing models of planetary formation, stellar chemistry, and the diversity of cosmic processes. In this sense, the lingering visitor is both a participant and an emissary, its presence offering opportunities for scientific insight that transcend immediate safety considerations. Risk assessments also include the possibility of artificial or engineered characteristics, as suggested by Loeb's hypothesis. While speculative, the consideration prompts careful monitoring for electromagnetic emissions or anomalous signals, ensuring that any unexpected behavior is detected early. Such vigilance is standard scientific prudence, illustrating how curiosity and caution intertwine in the study of extraordinary phenomena. Even if the artificial hypothesis proves unfounded, the framework for analysis strengthens observational protocols and refines techniques for future interstellar encounters. Ultimately, the significance of 3I Atlas lies less in immediate hazard than in its ability to expand perspective. Its lingering presence serves as a tangible reminder of the dynamical complexity of the solar system, the subtle interplay of gravitational and non-gravitational forces, and the potential for objects from distant stars to influence our local environment. By studying its trajectory, composition, and interactions, scientists gain not only data but philosophical insight. The universe is alive with movement, connection, and possibility, and even a solitary interstellar visitor can illuminate the intricate, often delicate, fabric of cosmic order. Beyond the scientific implications, 3I Atlas evokes profound cultural and philosophical resonance. Humanity has long looked to the stars for guidance, reflection, and narrative, and the arrival of an object from beyond the sun's sphere invites contemplation about our place in the cosmos. Its presence, lingering yet distant, acts as a mirror to human curiosity and imagination, prompting questions about origin, purpose, and the broader interconnectedness of all celestial phenomena. Artists, writers, and philosophers may find inspiration in its journey, translating orbital mechanics into metaphors of exploration, isolation, and discovery. The emotional impact extends to scientists themselves. Observatories filled with blinking instruments and quiet hums of cooling systems become spaces of reverent observation where data points acquire a narrative dimension. Each rotation, each subtle acceleration, each reflective facet observed is a fragment of a story billions of years in the making. Astronomers report a sense of awe, not merely at the rarity of detection, but at the intimacy of observation, watching a solitary traveler navigate gravitational corridors that, by coincidence or cosmic design, intersect with human curiosity. The object becomes simultaneously a puzzle and a companion, a participant in a dialogue spanning light years and eons. Culturally, 3I Atlas bridges science and imagination. Ancient civilizations interpreted celestial anomalies as omens, messages, or divine expressions. Today, such interpretations are filtered through empirical observation and theoretical modeling. Yet, the fundamental human response remains: wonder at the unexpected, reflection on the unknown, and an urge to contextualize our small world within a vast, complex universe. The visitor's lingering presence evokes humility, reminding observers that despite our technological and intellectual achievements, the cosmos retains its capacity for surprise, challenge, and insight. Philosophically, the object's path invites meditation on transience, permanence, and perspective. Unlike earthbound events that unfold on human timescales, the movements of interstellar objects operate over millennia and light years, forcing reflection on temporality and the scale of existence. 3I Atlas lingers in a liminal space, neither fully integrated into the solar system nor simply passing through, offering a tangible symbol of thresholds, transition, and the interplay between chance and order. In contemplating its presence, humanity engages with questions both scientific and existential, bridging observation and introspection in a uniquely cosmic dialogue. Loeb's broader theories on interstellar objects contextualize 3I Atlas within a universe teeming with potential messages and probes. In his perspective, objects traversing between star systems might not be mere fragments of distant planetary formation, but deliberate carriers of information, vestiges of intelligent processes elsewhere in the galaxy. While controversial, this framework reframes the discussion from passive observation to an active search for meaning, encouraging the scientific community to consider whether interstellar objects could serve as natural conduits of discovery, revealing both physical properties of distant systems and hints of advanced civilizations. Applying this lens to 3I Atlas, the lingering trajectory takes on new significance. If it remains within the solar system longer than expected, it provides extended opportunities for study, enabling more detailed spectroscopic analysis, precise tracking of rotational dynamics, and careful searches for electromagnetic emissions or other indicators of engineered structures. Loeb suggests that even subtle anomalies, unexpected reflectivity patterns, unexplained accelerations, or unusual surface composition could potentially align with characteristics one might anticipate from interstellar probes designed to endure long voyages across space. Each data point, then, becomes part of a broader interpretive framework, not merely natural phenomena, but potential signatures warranting careful, rigorous inquiry. These ideas intersect with broader SETI, search for extraterrestrial intelligence, considerations. Traditional approaches have focused on detecting distant radio signals or megastructures, but interstellar objects like 3I Atlas offer a tangible, physical target within reach of observation and analysis. By integrating orbital dynamics, composition, and subtle anomalies into predictive models, researchers can assess whether any observed characteristics deviate from natural expectations in ways that merit further investigation. Loeb's approach emphasizes that the search for intelligent processes need not be purely speculative. It can be grounded in empirical data, systematically tested, and contextualized within the framework of known astrophysics. Ultimately, 3I Atlas under this paradigm becomes more than an interstellar wanderer. It serves as a catalyst for expanding the scope of inquiry. Its presence encourages the scientific community to consider the full spectrum of possibilities, natural and artificial, without abandoning methodological rigor. Even if subsequent observations confirm a wholly natural origin, the exercise sharpens observational techniques, refines theoretical models, and underscores the richness of inquiry that arises when an object defies easy classification, prompting scientists to question, explore, and expand their understanding of the universe and its potential inhabitants. In conjunction with Loeb's hypotheses, targeted searches for communication or signals from 3I Atlas became a focus of specialized observational efforts. Radio telescopes, ranging from the Green Bank telescope in the United States to arrays in Europe and Asia, were tasked with scanning a wide range of frequencies for anomalous emissions. These observations sought to detect electromagnetic signals that could indicate artificial activity or interactions beyond those expected from natural processes. While no definitive artificial signal has been observed, the exercise sharpened methodologies for identifying subtle anomalies amid the vast cosmic background, refining techniques for differentiating noise from potentially meaningful patterns. Simultaneously, multi-wavelength studies extended to high-energy observations, including X-ray and gamma-ray monitoring. These efforts aimed to detect transient emissions that might correlate with rotational periods, surface features, or interactions with the solar wind. While no high-energy signals consistent with artificial activity were identified, the data provided invaluable constraints on the physical and chemical processes occurring on or near the object's surface. By systematically eliminating certain possibilities, researchers were able to narrow the range of plausible explanations, highlighting the iterative and cumulative nature of scientific investigation. Beyond direct searches for artificiality, these efforts contributed to a broader understanding of interstellar materials and dynamics. Any transient or unexpected emissions, even if natural, offered insight into surface composition, response to solar radiation, or interactions with interplanetary media. The multimodal approach, combining optical, infrared, radio, and high-energy observations, created a comprehensive dataset unprecedented for an interstellar object, allowing cross-validation of anomalous behaviors and improving confidence in derived physical parameters. Philosophically, the pursuit of signals embodies humanity's enduring curiosity and desire to connect with the unknown. Whether or not 3I Atlas harbors artificial characteristics, the exercise reflects an expansion of observational ambition, pushing the boundaries of what can be detected and analyzed. In scanning for potential communication, scientists engage not only with data, but with imagination and possibility, bridging empirical rigor and speculative inquiry. The endeavor reinforces the object's dual role as both a natural phenomenon and a canvas for exploring the deepest questions of presence, origin, and intelligence beyond our solar neighborhood. The scientific lessons derived from 3I Atlas extend beyond its immediate characteristics, offering insights into broader astrophysical processes and methodologies. Foremost, the object challenges assumptions about interstellar object populations and behaviors. Prior models treated interstellar visitors as rare, small, and fleeting, yet 3I Atlas demonstrates that larger, more complex bodies can traverse vast distances and potentially linger, prompting reconsideration of the statistical prevalence and diversity of such objects. This has implications for models of planetary system formation, stellar ejection mechanisms, and the material composition of distant star systems. Additionally, 3I Atlas serves as a case study in the integration of multimodal data, combining astrometry, photometry, spectroscopy, thermal imaging, and computational simulation exemplifies the power of a holistic approach to celestial analysis. Each dataset informs and constrains the others, creating a self-consistent model of shape, motion, and composition. The exercise underscores the importance of collaboration across observational platforms and disciplines, demonstrating that complex cosmic phenomena often require the synthesis of diverse perspectives to be understood effectively. The object also illuminates the interface between theory and observation. Its anomalies necessitated not only recalculation of gravitational models, but also the exploration of unconventional physics and speculative mechanisms. This dual approach, grounding hypotheses in known laws while remaining open to extensions when data resist explanation, illustrates the iterative nature of scientific progress. Researchers are reminded that anomalies are opportunities, moments when observation outpaces expectation and when curiosity can drive both theoretical refinement and technological innovation. Finally, 3I Atlas offers lessons in scientific humility. Despite advances in instrumentation, computational modeling, and global coordination, the universe continues to present surprises that defy easy categorization. Each new interstellar object encountered is a test of understanding, a challenge to integrate data, theory, and imagination coherently. In studying 3I Atlas, astronomers reaffirm that observation, meticulous analysis, and openness to unexpected phenomena remain essential tools, guiding humanity's ongoing exploration of the cosmos and deepening appreciation for the intricate, dynamical tapestry in which even a solitary visitor can have profound significance. Speculation about the potential futures of 3I Atlas offers both scientific and philosophical intrigue. If the object continues to linger, even temporarily, its trajectory may evolve under the cumulative influence of the Sun, planets, and minor gravitational perturbations. Over decades, subtle shifts could either stabilize a quasi-bound orbit in the outer solar system or eventually redirect it into a path leading back toward interstellar space. These long-term projections rely on precise modeling of all forces at play, highlighting the sensitivity of interstellar dynamics to initial conditions and minor accelerations. The object's ultimate fate remains uncertain, a cosmic narrative unfolding on timescales that dwarf human experience. Various scenarios have been explored. One possibility involves repeated interactions with Jupiter and Saturn, gently modulating the orbit to maintain temporary retention. Another anticipates gradual escape, where minor accelerations from radiation pressure or outgassing eventually overcome gravitational ties. Some models even entertain low-probability, high-impact events such as a close encounter with a trans-Neptunian object that could alter trajectory abruptly. While collision risk with planets remains negligible, these theoretical exercises illuminate the complexity and unpredictability inherent in interstellar travel and solar system dynamics. Beyond mechanics, speculation extends to observational opportunities. The object's lingering presence allows prolonged monitoring of rotation, spectral features, and potential emissions, providing an unprecedented window into interstellar material. Each measurement refines models, constrains hypotheses, and may reveal surprises unanticipated by current frameworks. The extended timeline permits iterative testing of theories about composition, structure, and subtle accelerative forces, enhancing the depth and resolution of scientific understanding. Philosophically, contemplating these potential futures reinforces the narrative of interconnectedness and chance. 3I Atlas, originating from an unknown star system, now interacts with our solar system in ways that are both predictable and uncertain, governed by physical laws yet sensitive to minute variations. Its journey exemplifies the delicate balance between determinism and contingency, and humanity's role as observer underscores the temporal and spatial scales that shape cosmic storytelling. In tracing these speculative pathways, scientists and philosophers alike engage with the profound interplay between order, anomaly, and the unfolding mysteries of the universe. The classification of 3I Atlas within existing astronomical taxonomies has sparked debate, illustrating the challenges of integrating an unprecedented object into structured knowledge systems. Traditionally, interstellar visitors are designated as transient, hyperbolic bodies passing through the solar system without lingering and catalogued separately from solar system comets, asteroids, or dwarf planets. 3I Atlas, with its unusual trajectory, potential quasi-bound orbit, and enigmatic physical properties, resists simple placement. Its characteristics blur conventional boundaries, suggesting the need for an expanded or modified classification scheme that accommodates objects capable of lingering while retaining their interstellar origin. Astronomers have considered multiple frameworks. One approach is to treat 3I Atlas as a quasi-bound interstellar object, emphasizing its transient but extended residence in the solar system. This category would acknowledge both its external origin and the dynamical interactions that allow temporary retention. Another proposal integrates morphological and compositional attributes, creating a subclass of interstellar bodies characterized by elongated shapes, reflective surfaces, and anomalous accelerations. Such a system would facilitate comparative studies, allowing future discoveries to be systematically assessed against known cases and anomalies. Classification has practical implications as well. Accurate categorization informs observational priorities, guides the development of predictive models, and shapes public communication of scientific findings. By defining categories that reflect both origin and behavior, astronomers can standardize reporting, enabling rapid comparison between objects and fostering international collaboration. It also encourages a proactive stance. As new interstellar bodies are detected, the taxonomy can accommodate novel features rather than forcing artificial fits into pre-existing categories. Beyond technical concerns, classification carries symbolic weight. Naming and categorizing celestial phenomena reflects an attempt to impose conceptual order on a universe that often resists simplification. 3I Atlas challenges these conventions, reminding observers that categories are provisional, contingent on current knowledge, and sometimes inadequate to fully capture nature's complexity. By grappling with classification, scientists engage not only with data, but with the philosophy of knowledge itself, balancing rigor, clarity, and humility in the face of a universe that continually surprises. Scientific philosophy and skepticism play a pivotal role in interpreting 3I Atlas, shaping both methodology and discourse. The object's anomalies, unusual trajectory, non-gravitational accelerations, irregular shape, and reflective properties challenge the limits of conventional models, prompting rigorous evaluation of observational techniques, data analysis, and theoretical assumptions. Skepticism acts as a safeguard, ensuring that interpretations remain grounded in evidence and that extraordinary claims are weighed carefully against empirical constraints. It is the lens through which anomalies are assessed, guiding the balance between open-minded exploration and methodological discipline. The philosophical dimension arises from confronting the unknown. When a single object defies neat categorization, scientists are compelled to reflect on the nature of explanation, probability, and inference. How much deviation from expectation justifies alternative hypotheses? What constitutes sufficient evidence to reconsider foundational assumptions in celestial mechanics or material science? In grappling with these questions, astronomers navigate the interface between certainty and curiosity, acknowledging both the provisional nature of knowledge and the imperative to explore anomalies that may illuminate previously unseen aspects of the cosmos. Skepticism also influences collaboration and communication. Debates regarding 3I Atlas, whether in peer-reviewed journals, conference discussions, or interdisciplinary workshops, highlight the value of critical dialogue. By challenging interpretations, proposing alternative explanations, and rigorously testing models, the community collectively strengthens the reliability of conclusions. This iterative process exemplifies the scientific method, demonstrating that the presence of anomalies does not signal disorder, but an opportunity for refinement, insight, and discovery. Ultimately, the engagement with 3I Atlas reflects the dynamic interplay of doubt and wonder. Skepticism tempers enthusiasm, but it does not extinguish curiosity. Instead, it frames inquiry in a disciplined yet imaginative context, where hypotheses are tested rigorously, data are scrutinized meticulously, and philosophical reflection enriches scientific exploration. In observing, modeling, and debating 3I Atlas, humanity confronts the limits of knowledge, the subtleties of evidence, and the enduring capacity for both humility and awe in the face of a universe that is vast, complex, and often enigmatic. The presence of 3I Atlas invites contemplation of the broader cosmic perspective, situating a single interstellar object within the vast scales of space and time. While humanity has historically measured existence in years and centuries, the movement of such an object spans millennia and light years, bridging distant stellar systems with our own. Its journey, originating perhaps millions of years ago in a far-off planetary system, now intersects with human observation for only a brief interval, emphasizing the ephemeral nature of our perspective and the permanence of cosmic processes. This contrast between temporal scales evokes a profound sense of humility and wonder, underscoring the relative brevity of human awareness against the backdrop of galactic history. From a spatial standpoint, 3I Atlas traverses distances that dwarf planetary scales, passing through gravitational fields, solar radiation environments, and interplanetary debris with apparent precision. Its trajectory, shaped by both deterministic mechanics and subtle non-gravitational influences, exemplifies the delicate choreography of celestial dynamics. Observing such a traveler highlights the interconnectedness of stellar systems, where objects expelled from distant stars may journey across the galaxy, carrying with them chemical and physical records of environments far removed from our own. Each observation thus becomes a link in a chain, connecting the Milky Way's complex tapestry of matter and energy. Considering this cosmic perspective also enriches the philosophical appreciation of 3I Atlas. The object serves as a tangible reminder of the vastness beyond our immediate solar environment, a messenger of scale and temporality. Its lingering path prompts reflection on the interconnectedness of matter, the flow of time, and the universality of physical laws across space. In observing and modeling the object, scientists engage in a dialogue with the cosmos itself, measuring, predicting, and contemplating, bridging the ephemeral human moment with the enduring motions of celestial bodies that have traversed interstellar distances over unfathomable spans. Ultimately, the cosmic perspective transforms 3I Atlas from a mere observational target into a narrative of connection and scale. It illustrates the vast distances, extended durations, and intricate gravitational and physical interactions that shape interstellar travel. Humanity's engagement with such an object becomes an exercise in contextualizing our place in the galaxy, acknowledging both the limits of perception and the expansive arena in which these extraordinary phenomena unfold, providing both scientific insight and existential reflection. Beyond the empirical and theoretical, 3I Atlas resonates deeply with human emotion, shaping responses that intertwine curiosity, awe, and humility. Observers frequently describe a sense of intimate connection to this distant traveler, despite the vast physical separation. Each rotation, each subtle deviation from predicted motion feels like a message encoded in light and movement, a testament to processes that have unfolded over millions of years across interstellar space. The emotional resonance emerges from both the rarity of the encounter and the profound implications it carries for understanding the universe as a dynamic, unpredictable, and interconnected system. The human fascination with 3I Atlas reflects a long-standing cultural pattern. Celestial anomalies have historically inspired myths, philosophical inquiry, and scientific advancement. The object's lingering presence evokes reflections on isolation, journeying, and persistence qualities mirrored in human experience. Observatories and laboratories, often quiet and austere, become spaces where this emotional engagement is permitted alongside rigorous analysis. Astronomers experience a combination of meticulous attention to data and contemplative reflection on the broader significance of the visitor, acknowledging both the constraints of current understanding and the poetic mystery of its existence. Emotion also intersects with the narrative of discovery. The identification of subtle accelerations, the analysis of spectral composition, and the refinement of orbital simulations produce moments of tension and anticipation. Each new measurement holds the promise of insight, a potential revelation that may clarify or deepen the enigma. This emotional rhythm parallels the scientific process itself. Moments of doubt and frustration, interspersed with exhilaration at uncovering patterns, confirming predictions, or observing anomalies that challenge expectations. The journey of studying 3I Atlas is thus simultaneously intellectual and affective, merging analytical rigor with the intrinsic human response to wonder. Ultimately, the lingering interstellar object serves as a mirror for human consciousness, reflecting our desire to understand, to connect, and to contextualize ourselves within a cosmos that is vast, complex, and often indifferent. Its presence inspires contemplation of scale, duration, and the interplay between the known and the unknown, reminding humanity that the universe is not merely a backdrop for observation but an active, intricate tapestry in which we are both participants and witnesses. In embracing the emotional resonance of 3I Atlas, science and wonder converge, producing a richer, more holistic engagement with the cosmos. As the observation of 3I Atlas progresses, a profound philosophical and reflective dimension emerges, complementing the empirical and theoretical analyses. The object, originating from a distant star system and now lingering within the gravitational embrace of our solar system, serves as a symbol of both the vastness and the intimacy of the universe. Its journey, spanning millions of years across interstellar space, intersects with humanity's brief observational window, offering a rare opportunity to witness cosmic history unfold in real time. This intersection invites contemplation on the nature of existence, the transience of human life, and the continuity of cosmic processes that operate on scales far beyond everyday perception. The philosophical resonance is enriched by the object's anomalies, the subtle accelerations, the irregular shape, the reflective properties that defy simple explanation. These features highlight the limitations of current understanding, reminding observers that even well-established physical laws operate within a broader and often unpredictable context. By confronting anomalies with rigorous observation, simulation, and analysis, scientists participate in an iterative dialogue with the universe, testing assumptions while remaining open to the unexpected. In this sense, 3I Atlas becomes both a subject of study and a mirror reflecting humanity's intellectual curiosity, adaptability, and humility. Reflective consideration also extends to the broader implications for human understanding of the cosmos. The lingering presence of 3I Atlas challenges preconceptions about interstellar object dynamics, composition, and origin. It invites inquiry into the possibility of interstellar probes, the diversity of material and chemical processes in distant star systems, and the delicate gravitational choreography that allows such objects to persist temporarily within the solar system. Each aspect of its behavior, from photometric fluctuations to trajectory anomalies, enriches not only the scientific dataset, but the conceptual frameworks through which humans interpret celestial phenomena. Ultimately, 3I Atlas embodies the interplay of observation, theory, and reflection. Its presence encourages meticulous study, speculative reasoning, and philosophical contemplation in equal measure. The object's journey reminds us that the universe is simultaneously comprehensible and mysterious, structured and surprising. As it continues its path, lingering yet ephemeral, humanity is granted the privilege of witnessing a narrative that spans space and time, connecting distant stellar origins with the immediacy of conscious observation. In this convergence, science, wonder, and reflection unite, leaving enduring questions, profound insights, and a quiet sense of awe at the vast, intricate cosmos in which we reside. As 3I Atlas slowly drifts through the outer reaches of our solar system, its presence becomes a gentle reminder of the vastness and subtlety of the cosmos. The object, silent and distant, continues its intricate dance under the sun's faint gravitational pull, a traveler whose journey spans light years and eons, intersecting with humanity's fleeting window of observation. Each rotation, each glimmer of reflected light speaks to processes that unfolded long before humans existed and will continue long after, a testament to the continuity and resilience of celestial motion. In contemplating its path, one senses both the enormity of time and the intimacy of engagement, as if the universe has offered a rare glimpse of its hidden mechanisms. The lingering anomalies, the subtle accelerations, the irregular shape, the unusual reflectivity invite ongoing inquiry while simultaneously fostering quiet reflection. They illustrate the delicate balance between predictability and mystery, reminding us that even in a universe governed by physical laws, surprises await the attentive observer. The object's journey bridges the known and the unknown, the measured and the speculative, prompting humility and wonder in equal measure. It exemplifies how observation, theory, and imagination converge, guiding scientific discovery while enriching the human experience of awe and contemplation. As the solar system continues its slow, silent motion, 3I Atlas remains a sentinel of the interstellar realm, a visitor whose story is both tangible and enigmatic. Its presence encourages patience in observation, rigor in interpretation, and openness to possibility, embodying the profound lessons of cosmic exploration that the universe is vast, interconnected, and often stranger than we expect. As we watch, calculate, and reflect, there is a quiet reassurance in knowing that each discovery, each anomaly, deepens understanding and connects us to the grand narrative of space, time, and existence. In the calm of the night, under the distant stars, 3-eye Atlas whispers of the endless journey beyond, inviting contemplation, wonder, and enduring curiosity. Sweet dreams.